Hi. In the previous video, we've learned basics of Leontief Input-Output Model. So now let's do an example where we can actually use what we learned to find the solution. Okay, so let's just say that the economy we are considering have just 3 sectors. So this is an input coefficient matrix for this economy. And here you see the specific values. So what we can learn from this matrix? We know, for example, that in order to produce $1 worth of good 1, we need to use 40 cents worth of good 2. In order to produce 1 unit of good 2, we need to use $1 worth of good 2. We need 10 cents worth of good 2. Okay, so as you see, those we have the same interpretations we discussed previously. Now that we've got numbers, we can check if everything makes sense. What should make sense here is that, for example, neither of these numbers should be bigger than 1, which is of course the case here. But what is more, the sum of those numbers should be always lower than 1. And we've got 0.7 here, which is good, 0.7 and 0.6, which means that all the sums here are below 1 the way it should be. Also, we are given a vector of final demands. You can always think about it not as 10 units, but like 10,000 units. These are the values that of final goods 1, 2, and 3 that's going to be purchased by customers. Okay, so now let's find what levels of production will be prevalent in the economy given those technical coefficients and final demand vectors. Okay, so we learned that in order to deal with this, we need to first find Leontief matrix given by I minus A times X will be equal to D. Okay, so let's start by writing down this matrix. And look, it's not that complicated here, right? All we need to do is from each of those, we need to change everything that is outside principal diagonal to negative values. And here we need to have 1 minus this, 1 minus this, and 1 minus this. So over here we will have 0.8, over here negative 0.3, and negative 0.2. Then we will have negative 0.4, then 1 minus 0.1 is 0.9, and negative 0.2. Then we will have negative 0.1, negative 0.3, and negative and 1 minus 0.2, which is 0.8. Okay. Now we've got vector of levels of production for 2 goods, so x1, x2, and x3. And vector of final demands 10, 5, 6. Okay, so look, now that we've brought this to the following form, matrix notation, we can start finding the solution. But of course, in order to find the solution, we need to solve this equation. We know that the vector of results is given by inverted Leontief matrix times vector of final demand. right? So what we need to do over here first is to check whether we can find inverted Leontief matrix. So what we would do here is to find determinant A, right, of determinant of Leontief matrix, and if it's different than 0, then we know we can find equilibrium solutions. Okay, in this particular case, value of the determinant is equal to 0.384. This is definitely bigger than 0 and different than 0. So we know that the solutions exist. However, this is not the only requirement for the model to make sense. What am I talking about here? Look, what if x2 would turn out to be -7? That would be clearly problematic, right? Because the level of production can be 0, definitely can be positive, but it never can be negative. So we need to rule out this option. And to rule out this option, we use Hawkins-Simon condition. And it goes like this. Given an n by n matrix B, this is our matrix B in this case, so Leontief matrix, with Bij lower than 0, off diagonal, right? When I is different than j, so off diagonal. So look, this is our matrix. Everything here is negative except for the principal diagonal. And n by 1 vector D, where everything is possible, positive or bigger than or equal to 0, which again, it confirms. Because of course, remember, on final domain we can have 0 in one of the places, but it doesn't change anything. Here, there exists an n by 1 vector x with only positive or 0 values, so with only non-negative values, such that b times x equals to d. If and only if the leading principal minors of B are all positive. Okay, so here we've got this matrix, the determinant B, matrix B, for which we will be calculating first principal minors. What are those first principal minors? Actually, this is very easy to explain. I'm going to show you this like that. So let's just say that we've got some matrix B for which we calculate the determinant. And let's just say it is 3 by 3, so it's just like in our case. B11, B12, B13, B21, B21, B22, B23, B31, B32, B33. Okay, now, what are the first principal minors? First principal minor you get by taking a first square out of any determinant with different sizes. So first we will have a square like this. So it's going to take up the first element. So first principal minor, which we will call B1, in our case is simply equal to B1. Then the second principal minor, B2, is given by the second square. So in our case, it is determinant of, because of course here it's also determinant, but it's just one element, 1, 1, B, 1, 2, B, 2, 1, B, 2, 2. We calculate this, and this is our second principal minor. And I hope you can guess the third principal minor is going to be the third square, which in our case is simply equal to the entire determinant. Okay, so knowing this, let's check if Hawkins-Simon condition works. It requires that all these three, so all the principal minors are positive, and then we can be sure that x1, x2, and x3 are positive. Okay, so in our case, B1 is equal to 0.8, which is clearly positive. B2, right, because this was, this is our B1. This is our B2. B2 is 0.8 minus 0.3 minus 0.4, negative 0.4 is 0.9. Okay, and we get that this is 8 times 9 is 72 minus 0.12, it is 0.6. Again, it is bigger than 0. And finally, B3, so third principal minor, is the entire determinant. So this is something we already established. It's equal to 0.384. It is bigger than 0. So, because it's bigger than 0, we know that Hawkins-Simon condition is met. And as a result, we know that not only solutions exist, but also they are positive, the way we want it. Okay, so having this done, we are ready for the most unpleasant step in this analysis, which is matrix inversion. And look, technically speaking, we could solve this using Cramer's rule, but it's extremely inconvenient in here. For various reasons. One of those is that if we will not find inverted matrix, Leontief matrix, we will have to repeat this process every time that vector of final demands is changing, which is very problematic, especially when you need to do it on your test. Okay, so look, first thing we need to do for our Leontief matrix is to find a matrix of cofactors. So we start with cofactor 1, 1, which is given by negative 1 to the power 1 plus 1, right? Okay, I'm gonna write this like this at the beginning. Later I'm gonna make it shorter because it's just gonna be troublesome. And this is what we get after deleting first row, first column. So it's 0.9, negative 0.2, negative 0.3, 0.8. Okay. So this is 0.72. Well, this is just 1. So 0.72 minus 0.6, which gives us 0.64. Okay, then we will have C1, 2, right? So this is negative 1 to the power 1 plus 2 times, if I delete first row, second column, I got negative 0.4, negative 0.1, negative 0.2, 0.8. Okay, so this gives us 0.32 negative, right? Minus 0.2, so it's negative 0.3, so it's 0.34, right? Okay, let me check. It's really easy to make a mistake in this. Okay, so we move further. Okay, now we know that this one will have plus at the beginning, right? So we can just start by eliminating first row, last column. It uses negative 0.4, negative 0.9, negative 0.1, negative 0.3. Okay, and out of this one we get that this is 0. Okay, I'm gonna write this because I'm gonna at some moment I'm gonna start making mistakes. It's 0.12 plus 0.09. Plus, yeah, it's 0.21. Yeah, okay, then we move to the second row. So here again, we're gonna have minus up front. Remember, if here's a plus, here's must be minus up front. Makes perfect sense. Okay, and if I delete the first row, second row, first column, because now we're talking about this element, I got negative 0.3, negative 0.2, negative 0.3, 0.8. So this gives me negative 0.24 plus minus 0.6, it's 0.3. Yeah, okay. Then we got C22. So this one we're going to start with plus, and we've got here 0.8, negative 0.2, negative 0.1, and 0.8, which gives us 0.62. Okay, then we move to C23. This one is going to start with minus, and we've got 0.8, negative 0.3, negative 0.4, I'm sorry, negative 0.1 and negative 0.3, negative 0.24 plus negative minus, so this is going to be 0.27. Okay, let me just check it. Yeah, everything works fine. Okay, then we've got C31. And we've got C31. So we eliminate it. So we delete, of course, first we will have plus. We delete third row, first column, and we've got negative 0.3, negative 0.2, 0.9, negative 0.2. So this gives us 0.06, plus 0.18, this is 0.24. Okay, C32, this one starts with the minus, and we've got 0.8, negative 0.4, negative 0.2, and negative 0.2. So we've got 0.16 minus 0.8, so it's 0.24, and C33 starts with the plus 0.8 times negative no, then 0.4, 0.9. So this one we've actually calculated right at 0.6. Okay, let me just make sure that we didn't make a mistake. Yeah. Okay, and now I can put it all together into a cofactor matrix. Okay, what we don't need? We don't need this. We don't need this. Okay, so cofactor matrix here is 0.64, 0.34, 0.21, 0.3, 0.62, 0.27, 0.24, 0.24, and 0.6. And then we've got that adjoint. So adjoint I minus A, adjoint the Leontief matrix, which is equal to C prime, is given by 0.64, 0.34, 0.21, then 0.3, 0.62, and 0.27, 0.24, 0.24, and 0.6. So finally, we get that inverted Leontief matrix, which is equal to 1 over the determinant times adjoint of that matrix is equal to 1 over 0.384 times 0.64, 0.3, 0.24, 0.34, 0.62, 0.24, and 0.21, 0.27, 0.6. Okay, so this is inverted Leontief matrix. So as I hope you can see that we are extremely close to find the vector of solutions. Okay, so what we do now is that we've got vector x, right? And this vector x with our solutions x1, x2, and x3 is equal to inverted matrix, Leontief matrix, times vector d, which is 1 over 0.384. Okay. Times 0.64, 0.34 times 0.21, 0.3, 0.24, 0.62, 0.27, 0.24, 0.6. Oh, and now what we need to do is to multiply inverted matrix, Leontief matrix, by vector of final demands. Okay, and unfortunately this is a very unpleasant and very time-consuming exercise that it's better done with a calculator. So let me just point that after the best way to do it is first to multiply those two, then we will get that this is times 954.794 and 705. And then if we divide by this and ignore spaces after the comma, we're gonna get that more than 2 places after the comma we get. This is 24.84, 20.68, 18.36. This is our solution. So these are the levels of production of good X1, X2, and X3 in the economy, where here is our input coefficient matrix, and this is vector of final demand. Okay, now why have I recommended so strongly that we do it by matrix inversion and not by Cramer's rule, for example? Well, look, the good thing is that once you have this inverted matrix A, inverted Leontief matrix, technical properties of this economy are not changing. But what can happen is, for example, you can have new vector of final demands. Like what if vector of final demands changes to 11, 7, and 3? Now look, having this, the only thing you would have to do is to substitute it in here and just calculate one last step, right? This is all you would have to do instead of starting from the beginning, like in the case of Cramer's rule, where you replace appropriate columns in the determinants. So, as you will also learn in the future, those coefficients have also some pretty good, this matrix has additional benefit of bringing us some comparative static information that we haven't considered quite yet. However, we're gonna do it in a couple of lessons. Okay, so now that you know how to solve it, there is one last question that remains unanswered in our examples. So, how much output is going for primary inputs? Okay, and look. So, in other words, what is the primary input required to maintain, to assure these levels of production? Okay, now, how do we calculate it? Well, what we need to do over here, is to use the outcomes that we've got. We've got x1, x2, and x3, right? But remember, they are simply levels of production of good 1, good 2, and good 3. How much was going to the primary input in the first sector? Well, I hope you remember that was 1 minus the sum of AIG with I equal to 1, and in our case is equal to 3, right? And we take, let's just say that we're talking about first sector. Look, we get that intermediate inputs take 0.7, right? So 0.3 is what goes to primary input, but it also depends on how much we produce, because this is for $1 worth. So if we are going to produce this much, we need to multiply it by appropriate level of production. So we're going to do it like this. We've got 3 sectors, right? So in each case, we need to find what part goes to primary inputs, and we need to add it up for all 3 goods. Okay, so what do we do here first? Look, in the first case, so for I equal to 1 and j equal to 1, we've got that this is 0.3 times level of production, which is 2484. Then we've got, in a second, we again get that to intermediate inputs it goes 0.7. So again we've got 0.3. This time times 20.68. And finally, in case of the third good, only 0.6 goes to the intermediate input, so 0.4 goes to primary input, and we multiply it by 18.36, which gives us, after rounding up, very nice number 21. And this is how much primary input is required in order to produce this much of each of the goods. Okay, so that's it for this week. We actually finished static at this moment. I've introduced to you 3 types of models over these 2 classes. During the next week, we're going to start comparative static. So we're going to compare 2 equilibrium states, and we're going to go back to all of these models, and we're going to squeeze some news information out of them using techniques that allow us for comparative static analysis. So thank you for your attention, and see you in the next video.